Alright guys, the next thing we want to be doing in calculus after differentiating polynomials, exponential functions and logarithmic functions is we want to be able to differentiate trig functions. And I realised that maybe before just going straight into how we differentiate them, I thought a nice Friday lesson might be just gaining a bit of understanding of what the trigonometry relationships are. So without further ado, we'll get into some trigonometry. So let's just construct a right angle triangle on this first page of our work. So a right angle triangle with some sort of angle theta. So from year 10 and year 11 trig, you know that there are three trig functions. What I would get you to do is you'd label this triangle. So obviously this is the hypotenuse. I should perfect this video. Hypotenuse. We have the opposite, and we have the adjacent. So, and we denote those with OA and H. So you know from basic right angle trig that there's three trig functions. So, and those come from, so what we looked at is ratios of sides. So we can take O over A, we can take O over H, and we can take A over H. And these were equivalent to, this was equivalent to taking tan of that angle, tangent of the angle. This was equivalent to taking the sine of that angle. And this was equivalent to taking cosine of the angle. So what I would got you guys to do in class is write down all the possible ratios of sides. So obviously someone just came up with O over A, took that ratio and called it the tangent ratio. But what if we took A over O? Now you're probably thinking, well, that's just tan inverse. And well, no, it's not. Tan inverse is the inverse function of tan. So if we had these sides, we would take tan inverse of those sides to get the angle. But what I'm saying is this is the reciprocal. So, and the reciprocal of tan theta is we call it cotangent theta or cot theta, and that is the reciprocal, isn't it? So it's 1 over. If we took the reciprocal of this, we'd have H over O, and so it's not sine. That's not a sine theta relationship. What is that one? That is cosec theta. So secant theta. Hopefully you can read that. Cosecant of theta, and we call that cosec theta, and that's obviously the reciprocal 1 over sine theta. Okay, so our last one is H over A. Now that's a reciprocal of cosine, sorry. So we call this one secant theta or sec theta, and that's just the reciprocal of the cosine function. So where's my red pen? We'll go through 1, 2, 3, 4, 5, 6 trig functions. So we have tan theta, sine theta, cosine theta, cot theta, so that's just 1 over tan, cosec theta or sec theta. Sometimes cosec is written as CSC for cosec. And the way I remember these, you won't have to remember them because you'll get a formula sheet. But I take the third letter of all these new ones, and that tells me what it's. This is just how I remember it. It tells me what it's 1 over. So cot is 1 over tan, cosec 1 over sine because of the s, and sec 1 over cosine. So the reciprocal is different to the inverse function. So with that, we can actually do some proofs. So I'm going to have a look at prove that if I take sine of any angle and divide it by cosine of any angle, of the same angle, that gives me tan of that angle. So let's have a look at that. So let's construct a right angle triangle. Try to do this really quickly. So let's get a right angle going. Here we go. Now, let's say we have this angle x and we have A, B, C. Then sine of x, that's O over H, isn't it? So that's B over C. Cosine of x, well that's A over H, so that's A over C. So therefore, sine x over cosine x is B over C divided by A over C. And you know, you keep change and flip if you're doing division by fractions. So you have B over C times C over A. C's cancel, you have B over A. Well, opposite over adjacent must be the tangent of that angle. So there we have it. Therefore, sine x over cosine x is equal to tan x. There's your first identity. Second identity, take the reciprocal of both sides. Cosine x over sine x is obviously 1 over tan x, and that is cotangent of x. And immediately a second identity falls out of that equation. So you might want to copy those down in your record of learning, and that was the quick proof going across here. Next one, proving a few things today, is we take a right angle triangle. So as I construct this right angle triangle, I'll mention that every shape can pretty much be constructed out of triangles, right? So like triangles are all used in construction a lot. You could take any polygon, break it down into triangles. So everything boils down to triangles in the end. Even circles, as I've shown you in conic sections, a circle is actually just taking this point around taking this point around any central point, and the hypotenuse is the radius of a circle. We've gone through that before. And then even the conic sections can be expressed parametrically in terms of trig functions. So I'm just going to make this triangle have a unit hypotenuse of 1 and a length A and B. And let's have an angle X. Sine X, well that's O over H, isn't it? B over 1. So in this one with a unit length for the hypotenuse, sine x is B. Cosine x is A over H, A over 1, which is A. And so by Pythagoras, we have A squared plus B squared equals 1. So that's just the same as saying sine x squared plus cosine x squared is 1. Because sine x is B, cosine x is A. And you'll notice in trig, we don't actually write it in brackets like this. It just takes too much time to put the brackets in. There's this new notation that we like to use, and that's sine x plus cosine 2 to the power of 2x equals 1. And that just means the entire thing has been squared. But that's just a bit of new notation. So those things mean the same. And there's another proof. So there's a third identity for us to use today. Okay, one more thing. We'll turn this page over. So there's this one as well. Let's create a right angle triangle. Okay. Right angle triangle. And let's see, make this an angle x, side A, sine C. So what must this angle here be? Well, this angle is 90 take away x, isn't it? 90 minus x degrees. Or, sorry, 90 degrees minus x. If this is x degrees. So just have to think about why that might be true. 180 take away 90, take away x, left with 90 minus x in that corner there. And we'll go A, B, C. Well, sine of x is b over c, isn't it? But cosine 90 minus x is b over c as well. So if I use this angle, adjacent over hypotenuse, cosine of this angle is b over c. Sine of this angle is o over h, so b over c. Well, that means that sine x is the same as cosine 90 minus x. And it also follows that cosine x is sine 90 minus x. That's why when we do trig graphing, that's why they're just out of phase by 90 degrees. So if you were to graph trig functions, that's why sine does this, and cosine starts either way you want to think about it, 90 degrees later or 90 degrees earlier, and it follows out of phase by 90 degrees. So that there is another identity. Okay. What I'm going to do now is I'm just going to show you that we use these in proofs, and they're quite useful because when we do derivatives of trig functions, sometimes we need to use some of these identities to either simplify the problem or to simplify the answer. So let's have a look at an example. Make sure that's lined up in the camera. Cool. So prove sine x times sec x times cotangent x or cot x, and we use these three equal symbols because it's not technically equal, it's equivalent to. Okay, so this just means equivalent to. So, well, note first that cot x is 1 over tan x. Well, that just means the reciprocal of tan, which means that instead of tan being sine over, which is sine over cosine, this will be cosine x over sine x. So we start the left-hand side, which is sine x, sec x, cot x. Well, that's equivalent to sine x times sec x times, and then we do this, we can replace the cot with cosine x, sine x, and notice those will cancel. Then we have sec x times cosine x. Well, sec is 1 over cosine, and there we have it, cosines cancel, we have the 1, and then we say that that is equal to the right hand side. And you can either use a little black box to say end of proof, or QED, quite easily done. No, it's actually Latin for something like this, quod erit demonstratum, something like that, which just fancy way of saying there it is. Right, so I'll do one more proof, so that might be a good one to keep in a record of learning, just as an example of how to go about the proof. I'll do another one, and then we'll probably leave it there for today. That's all lined up in the camera, okay? So, prove sec x over tan x is equivalent to cosec x. A lot of textbooks put the brackets around, but I get a bit lazy and I don't do it. It's kind of obvious, right? So we start left hand side is equal to sec x over tan x. Well, that's equal to sec x, and I just like to do this little step. Sec x divided by tan x. Well, sec is 1 over cosine x, and that's dividing by sine over cosine. And that's equivalent to timesing by the reciprocal. And then notice those are cancelled. We're left with 1 over sine. And now look at, well, I've got 1 over a trig function. That's going to be the third letter of that, one of those new trig functions. So that's going to be cosec, which equals the right hand side. Now you don't always have to start for left hand side. Sometimes it's easier to start here and go back. And then a little black box, or QED. Doesn't really matter, but don't do both. So did we, I might actually post some problems for you to try those trig proofs on. And do I want to do some further identities? I think I do. So we know what happens now is that we've proved a few smaller things. We then use those proofs to prove some other more bigger picture stuff. So let's have a look at sine squared x plus cosine squared x equals 1. So that just falls out from that Pythagorean theorem that we've done before. Well, what if we divide everything through by sine squared x? Then we have sine squared x over, start again, we have sine squared x over sine squared x plus cosine squared x over sine squared x equals 1 over sine squared x. And you'll be wondering why I've done this. Well, let's have a look at what happens here. Well, that's 1. This here, well, that's sine over cosine, isn't it? Would be tan. That's the reciprocal of tan. So this reciprocal of tan is cotangent, but it's squared. And that's equal to, well, that's cosec, isn't it? And that's cosec squared x. And so there's another identity. And then what we usually get on your formula sheet, it will have this identity written in the 3 separate ways. It will have cot squared x is equivalent to cosec squared x minus 1. And it will have cosec squared x equivalent to, and it will have cosec squared x take away cot squared x equivalent to 1. So these are all the same, but in your formula sheet for exams, you'll get given all 3. Awesome. So we divide by sine squared x, so you might want to copy those ones down. But what if we divide by cosine squared x? you're going to notice that all these sort of identities are going to be falling out, and then they're going to become quite useful for either simplifying a differentiation before you do the derivative, or simplifying the answer to a derivative function. So we start off this identity, and then let's divide through by cosine squared. So I'm just dividing everything by cosine squared this time. Well, sine over cosine, well, that's tan, isn't it? So it's going to be tan squared. Oh, I realised that was meant to be cosine squared, isn't it? Plus 1, because that's something divided by itself, equals, what's the reciprocal of cosine? Sec. Secant. And it's squared. So there is another identity that you'll see on your formula sheet. And then they have all the iterations of rearrangement. So tan squared x is sec squared x minus 1, and sec squared x minus tan squared x is equivalent to 1. Should be equivalent. So there's 3 more. So in the space of 10 or 15 minutes, we've quite easily deduced quite a few trig functions. Okay, so with that, I'll do one last proof to end the day. Prove that 1 plus cot squared x, I'm going to do square brackets for these proofs, multiplied by, square brackets because these are usually put into curved brackets, 1 minus cosine squared x is equivalent to 1. Can we prove that? Well, left hand side, which equals, we rewrite the whole thing, I know it's a bit annoying, but it's this times that. Well, 1 plus cot squared, well, that was cosec squared, wasn't it? So that's actually cosec squared x from, I think it's on the back of this page. Yeah, so that equals this thing here. And this here, 1 minus cosine squared, well, that was sine squared x, isn't it? That's just from this one. Notice if I did 1 minus that, I had sine squared. So it's just a rearrangement of some of those identities. Well, that's going to be 1 over sine squared x times sine squared x. And so that's equivalent to 1, which equals the right hand side. I shouldn't be using those intermittently. We use equals through the proof, but we use the equivalent for the actual statement. Equals right hand side, Q, E, D, if you want to be fancy about it. And that's all we prove. So something that looks particularly gnarly to prove broke down very simply in the end. So say you were asked to differentiate this function. Well, you wouldn't know what to do, would you? But if you actually simplified it, you realise you'd actually just be differentiating a constant of 1. Say that was the answer to a derivative. Well, you can go ahead and simplify it right down, realise that it's 1, and you're done. So that's why we're going to spend a couple of days on these trig proofs. Nice.